All right. Continuing with our related rates problems. And I did notice a couple typos on my handout yesterday. I don't know why I even typed on number 18. The volume is 1/3 pi r square h. When I was looking over it last night, I immediately realized that's the volume of a cone. And this is not a cone we're talking about. This is a right circular cylinder. Even if I had not given you that formula, how could you find or develop the formula for volume of a cone, not a cone, a cylinder on your own? Think about what volume means and see if you can tell me what that formula would be without me having to give it to you. The area of the circle is what? Pi r squared, and then multiply that times the height of the cylinder, and that would give you the volume of the cone. So that formula should be just V equals pi r squared h, and that 1/3 is not supposed to be there. Make sure you fix that. All right, number 18 says the volume of oil in a cylindrical container is increasing at a rate of 150 cubic inches per second. Now we're trying to assign all the right variables and use all the right symbols. The first thing I notice is that 150 is a rate. So my symbol is going to be something over dt. And I just have to figure out what the something is. I can tell that by the fact that my units are cubic. So what's that a measure of? Or what symbol will I use for the rate of 150 cubic inches per second? That's a change in volume with respect to time. So I'm going to use, given that dV over dt is 150. And I'm not going to put the units, I have them highlighted. I can look back at that if I need to. What else am I given? The height is approximately 10 times the radius. How could you write that symbolically? H equals 10R. So that's what this sentence is telling me. At what rate is the height of the oil changing? That means find what? It's asking for a rate, so it's something over dt. What can we use for the rate at which the height is changing? That's dH over dt. And we're supposed to find the rate at which the height of the oil is changing, specifically when the oil is 35 centimeters high. So I should type in, which variable is that 35? Yeah, that's when H equals 35. The first thing you want to be able to do on every problem is write that sentence. And I put words in it. Given this and this, find this when blah. And that 35 is not a constant. The depth of the oil is changing throughout, so I'm not going to substitute it into the equation too early. I just want the equation volume equals pi r squared h. Except for there's one problem with that formula. How many variables does that formula have in it? 2. No. It has more than 2.
3.
It has 3 variables in it. Do we either know or are looking for all 3 rates? Which one rate do we know? Which is the volume. All right, we know the rate of change in the volume. And what rate are we looking for? Rate of change in the height. This equation has to be written in terms of only volume and height because that's what I know and what I'm looking for. In other words, I can't have R's in my equation. I have to have only V's and H's because those are the rates that are known and the rates that are to be determined. What can I put in place of that R?
The H equals.
Yeah, H equals 10R tells me R is 1/10 of H. And that's what I can put in the place of R so that I only have equations with the variable whose rate I know and the variable whose rate I'm looking for. So V equals pi times 1/10 H times squared, because R is squared, times the other H. So now my equation only has two variables in it. I would clean that up a bit before I differentiated. I would say that's V equals 1/100th pi H cubed. Okay. All right. When I have my formula in terms of only the variables whose rates I know or whose rates I'm looking for, then I'm ready to differentiate both sides with respect to t. What's the derivative of the left-hand side with respect to t? dv over dt. And what about the right-hand side with respect to t? I don't have R's, I have H's. Okay, so 3/100ths pi, and then subtract 1 from the exponent. Anything else? Anytime I take the derivative of a variable with respect to time, I'm going to have that symbol dH over dt as part of the derivative. Now, we're solving for dH over dt. I could either substitute numbers in for dV over dt and H and then solve for this, or I can solve for that before I plug the numbers in. It's usually easier to plug the numbers in first. So I'm going to go ahead and say dV over dt is 150. We're looking for the rate of change in height at the specific moment when the height is 35. And then 35 in the place of H times VH over dt. And then solve for dH over dt. I could divide that. Well, I think I'd multiply both sides by 100 to clear out the fractions. And then divide by the 3 and the pi and the 35 squared. Cleared out fractions and then divided by all the stuff that was with the dH over dt. And I went ahead and punched that on the calculator. I got it to be, well, it reduced to 200 over 49 pi. If you want an exact answer, if a decimal approximation is good enough, you can punch it on the calculator and get about 1.3 inches per second. I think the homework always says, and if it doesn't, I mean, always get the exact answer first, simplify it as much as possible. And then if you look in the back of the book and they have a decimal, just punch yours on the calculator to make sure it's equivalent to their decimal. On the test, I will try to always remember to tell you. And a lot of times I say the exact answer because I want to make sure that you, well, this one, there wouldn't be, I don't think, a way that you could get the decimal approximation without having the exact answer first, but on some word problems you could, especially anything with treating.
So that's exactly.
Yes. Yes, an answer with 3.14 plugged in the place of pi is never exact.
Yeah.
So, yeah, on the test, if I said exact answer, it would be this. If I say round to the nearest tenth, it would be that. All righty. And I'm not sure who just came in, but make sure you correct on number 18. I had a typo in that formula. It's not supposed to be 1/3 pi r squared h. It's just pi r squared h. All righty. I have so many papers. Number 20 is our next one. A trough. You grew up on a farm, you know what a trough is. You water your horses and cows in a trough. And that's my very best 3D rendering of one. A trough is 12 feet long and 3 feet across the top. Can you label that on your picture? I'd say probably that's my length of the trough is 12 feet and 3 feet across the top. That means this is 3, that's 3. And its ends are isosceles triangles with altitudes of 3 feet. You know what the altitude of the triangle is? Perpendicular to the base. So this is 3 feet as well. Find an equation for the volume of water in the trough in terms of only the water's depth or height. We can call the height of the water at any given time H. And we're trying to come up with a formula for volume in terms of height. Now, if I looked in the inside cover of my book, you think there'd be a formula for a trough, for the volume of a trough? No, there's no formula for volume of a trough in my book. So how would I come up with it? The area of the triangle times the length of the trough. Just like for this cylinder, it was the area of the base times the height of the cylinder. So what is the area of a triangle? Yeah, because any triangle is half of a rectangle, half of a rectangle. So you find the width of the rectangle or the area of the rectangle and then cut it in half. So the volume of that trough would be 1/2 the base times the height, and then multiply that times the length. Are any of those things constant? The base, the height, and the length of the water as that trough fills up. The base, well, when the water's low, the base is smaller than if the trough is full. So the base, the height definitely changes as I add water. The base of this little rectangle, the size of the rectangle at the end of the water changes, but what doesn't change? Yeah, as the water fills up the trough, the length of the water is always 12, no matter what the base and the height are. It's only the base and the height that are changing. All right, so because that doesn't change, I can put 12 in the place of L. Right now, this equation has 4 variables in it, and I can't differentiate it until it only has the variables whose rates I'm either given or am looking for. So can't have 3 variables on the right-hand side. I can put 12 in place of the length, but what about the base and the height? What do I know about the base and the height of the water at any depth? At that depth right there. Why are they the same? Because they're the same when the trough is full. When the trough is full, the water is going to be 3 feet deep and 3 feet wide. So at any depth, the base is the same as the height. The length of the length of the base is always, the length of the water is always 12, and base equals height. These instructions are telling me to get the equation so that it only has H's on the right-hand side. So what would I have on the right-hand side? One half, I can put H in place of the B, and then I have the other H, and then I have the 12. Yeah, I could clean that up to be 6H squared. I'm putting 12 in place of L, and I'm putting H in place of B. The volume of that trough is just 6 times however high the water is at any given moment squared. All right. Find an equation for the rate of change in volume. What does that tell us to do? That means differentiate. Anything that says find an equation for a rate of change is calculus. It's take the derivative. So the derivative of the left-hand side would be dV over dt. And the derivative of the right-hand side would be what? Perfect. So we have 2 different problems to solve now that we have a formula for the rate of change in volume. The A part is giving us the water pumped into the trough at the rate of 2 cubic feet per minute. What is that 2 cubic feet per minute? Rate of change in volume. And what symbol will we use for that? dV over dt. dV over dt is 2. How fast is the water level rising? Again, that's a rate because it says how fast. That means what symbol we'll use for what we're looking for. That's dH over dt. And we have to be given at some specific height or depth of the water. We're asked to find the rate of change in height when the height is 1. We're going to use this equation and say dV over dt is 2 equals 12 times the specific height is 1 times dH over dt, the thing we're looking for. Which reduces to 1/6. What's the units on that? What have we found? It's not cubic because that's not a change in volume. The height is just measured in feet. So it's feet per minute. 1/6 of a foot per minute. And here's the other typo I found last night. I had H equals 7 there. It's supposed to be H equals 2. If the trough is only 3 feet deep, I can't tell you how fast the water's rising when it's 7 feet deep. It's spilling over. So it's supposed to be a 2. The water is rising at a rate of 3/8 inches per minute. What's that a measure of? That's a change in height per minute. So it's a rate. And what symbol will I use for that rate? They're giving me dH over dt. That is 3/8. It says determine the rate at which the water is being pumped into the trough. That means find what? That's the rate of change in volume, dV over dt. And I'm given at some specific height, and the height is 2. So I'm looking for dV over dt. Using this equation, dV over dt is 12 times my particular height, which is 2, times the rate of change in height, which is 3/8. And I think that would be 9. What is that 9? Wait. Have I done something wrong? I have 12 times 2. Oh, I made a common mistake. Oh, so common. Gosh darn it. Oh, I made the mistake of hiding the whole problem from you. No, gosh darn it. And I did this problem last night and said, don't forget that. And I did. You see anything wrong with using 3/8 for dH over dt? Oh, darn. This was in, everything else was in feet. The trough is 12 feet long, 3 feet across the top, and the altitude of the end is 3 feet. I have to change, yep, gosh darn it. Where can I fit that? 3/8 inches per minute. I want to convert it to something that is feet per minute. So what do I have to multiply it by? Use your unit canceling. If you want to cancel out inches and leave feet, you have to have inches in the denominator and feet in the numerator, because that's what you want to be left with. So what's your unit fraction right there? 1 foot is 12 inches. And so 1 foot per 32. Yeah. I should have put 1/32 into that equation instead of 3/8. Well, that's 24 over 32, which is 3/8 divided by 4. No, I'm divided by 8. 3/4. 3/4. And what's the units on that 3/4? For units. That's a rate of change in volume. And how is volume measured? cubic feet per minute. Okay, doke. Gavin, is that good? All right. I got sucked down a rabbit hole last night because I had been using one website that had animations for related rates, and that website shut down. I don't know why. It was from Temple University and they took it down, but it was such good animations. So I started trying to find some other animations, and I discovered GeoGebra, which is, I knew about the website. Hold on. GeoGebra is wonderful. I just need to know how to use it better. So I was trying to figure out GeoGebra on my own last night. And I embedded into Momentum under test 3 notes. There's test 3 notes. I embedded related rates animations, and I started trying to edit these a little bit, and that's what I didn't know how to do very well. But let me show you this falling ladder animation, because the next problem that we have, number 22, is about a construction worker pulling a plank up the side of the building. So we can imagine that instead of a ladder, that's just a long board. And the way this is set up, the ladder is going to be falling down the side of the building. Our problem is going to be raising up, but it's the same general concept. I'm going to play this a couple times, and I want you to pay attention to something different each time I play it. This is set so that the x-axis is how far away from the base of the building the base of the ladder is. The ladder sliding along the ground here, and x is the distance the bottom of the ladder is from the building. Y is the height of the top of the ladder as it slides down the building. And the variable that is constant here is the rate of change in x. Somebody's pulling the base of the ladder along the bottom of the ground, and they're pulling it at a constant rate. Do you think the top of the ladder is falling down the building at the same rate, or is that rate going to change as the ladder goes down the building? I'm so bad at sometimes I think real life math applications. It's hard for me to say why that is. Can any of you tell me why you expect the ladder's top to be speeding up as it falls if the bottom is being pulled at a constant rate?
A lever, because a lever acts as when items connect to a base. As you get farther away from the base, it applies more force at the top.
Because you're pulling this is the constant
force to it, so this has no like weight going against it.
I still can't say
This is
that.
an engineering problem.
Huh?
It's an engineering problem.
I know, and I'm so bad at that. Okay, all right, let's watch. Let's watch this animation. First time we watch it, I want you to pay attention to the speed at which the bottom of the ladder is moving along the ground. You tell me whether that speed looks constant or if it looks like it changes. Kick the ladder. Does that bottom look like it's moving at a constant speed, or is it speeding up or slowing down? The bottom of the ladder? The bottom of, let's do it again. Reset. Watch only the bottom of the ladder and tell me if it looks like it's speeding up or staying the same speed. Yeah, that bottom of the ladder is sliding along the ground at 3 feet per second, I can change the speed, but whatever I set the speed to, that's how fast the bottom of the ladder is moving, no matter where the bottom of the ladder is. Now, I'm going to play it again, and I want you to watch the top of the ladder sliding down the wall. And tell me whether it seems to remain constant or speeding up. It's definitely speeding up.
Ladder shifts.
Okay, I got that. That's a pretty good way.
As it's like here, everything, the weight is all like this, but as it's moving, the weight's slowly shifting, so it's making this side go further down because the weight is going from this to this.
I almost got that. And for anybody to be able to explain that in a way that I even almost get is impressive. I know you are. Yeah. So dx over dt is constant. dy over dt is speeding up. All right. And to make it look like the problem we're fixing to do, oh, something I didn't tell y'all yesterday. Pay attention to whether a distance is increasing or decreasing, and make sure you include that in your rate. dx over dt is getting bigger because the bottom of the ladder is getting farther from the wall. Dx over dt has to be positive. But if the height of the ladder is decreasing, then dy over dt is negative. All right, so make sure you're watching out for that. In the problem where we're fixing to do where the construction wall, the construction worker is pulling the top of the ladder up the wall, it's going back this way. Is dx over dt going to be positive or negative? Is x increasing or decreasing? Decreasing, so dx over dt is going to be negative. And is dy over dt, or if we use h instead of y, is dh over dt positive or negative? It's positive. Okay. I'm going to leave these animations in momentum so you can click on them if you want to think about them some more tonight. They may help you with some of your other problems. Let's go back to the notes. Just made me want to take a workshop on using GeoGebra because it was so cool. All right, a construction worker pulls a 5-meter plank up the side of a building under construction by means of a rope tied to one end of the plank. So it really helps me to try to sketch that and label it with the variables I'm going to be using. This is a plank being pulled up the side of a building. That's my side of the building. Here's the plank. And what's not changing about that plank, no matter how high up or down the top of it is? The length of the plank's not changing. Don't label anything that's changing on your picture. Only label what's constant on your picture. And the length of that plank is a constant 5 meters. Assume the opposite end of the plank follows a path perpendicular to the wall of the building. Could have also said, assume the bottom of the plank bumps along the ground, because that's the path perpendicular to the building. The worker pulls the rope at a rate of 0.15 meters per second. Now, like the illustration that we just saw, if I let x be the distance of the bottom of the plank from the bottom of the building, then I can either let y or let h, whatever variable I want, be the top of the distance of the top of the plank to the ground. So what is that 0.15 meters per second? It's definitely a rate because it's per unit of time. It's the rate at which this is being pulled up. This is where dude or dudette is standing with the rope. And so that's dH over dt. Or I could have used y, doesn't matter. dH over dt is 0.15. And what we're asked to find is how fast the end of the plank is sliding along the ground. What symbol could we use for that? That's how fast X is changing. How fast X is changing is dH over dt. I said X, X is what I meant. X is what I meant. I said something different. Find dx over dt when, at some specific moment in time, when it is 2.5 meters from the wall of the building. What's that 2.5? That's an X, so when X equals 2.5. Now, there's one other thing I want to check before I try to come up with an equation. One of those rates, which quantity is getting bigger, X or H? H is getting bigger as the plank is being pulled up the building. What does that mean about dH over dt? If H is getting bigger? Well, it's going to be positive. So I'm right in having dH over dt is positive 0.15 because H is getting bigger. When I solve this, do I expect to find the dx over dt that's positive or negative? Negative, because X is getting smaller. All right. What equation would involve the X and the H and the 5? The area of the triangle really wouldn't depend on the 5. It would depend on just the X and the H. You said it.
Okay.
That's a right, assuming my building is standing straight up, assuming this is not the Leaning Tower of Pisa, then I can use the Pythagorean theorem and say x squared plus h squared equals 5 squared. It doesn't have anything about rates in it until I differentiate with respect to t. So the derivative of the left-hand side with respect to t would be what? Not necessarily.
If it's a right triangle.
No, we don't know that the x and the h are the same. They would be the same at some point. There are a lot of different numbers that can satisfy that equation. So no, it's not necessarily, it may be a 3, 4, 5 at some point, but then it's going to change as the dude or dudette pulls the plank up. All right, so what's the derivative of the left-hand side with respect to t? Equal to what? The derivative of 25 is 0. Now, just to get an equation that is a little bit easier to plug numbers into, I could divide both sides by 2. I don't have to, but it'll give me smaller numbers to work with when I start plugging in values. What I'm trying to find is dx over dt when x is 2.5. So I'm going to put 2.5 in place of x. And I'm solving for dx over dt, so I don't have to have anything in place of it. But I don't have anything to plug in the place of h.
Calculate the percentage.
When x is 2.5, I can find h. So maybe I need to do that over here. When x equals 2.5, h would be, what would I need to punch on the calculator to get h? X is 2.5. Square root of hypotenuse squared minus leg squared. Square root of hypotenuse squared minus leg squared. And I have punched that already. That's the square root of 18.75. I don't want to get a decimal approximation until I'm finished. So as an exact value, I'm just going to leave it square root of 18.75. And that's what I need to plug into h right here. What can I put in the place of dh over dt? That was my 0.15. I like to solve for dx over dt before I pick up my calculator. So what would I have to do to get the dx over dt by itself? I'd need to subtract the 0.15 times the square root of 18.75 and then divide by the 2.5. So sure enough, that's going to be negative like we expected it to be. I punched it on the calculator already and got that to be about negative 0.26. Now, what's that a measure of? That's a measure of this distance of the bottom, the rate at which this bottom of the plank is moving toward the building. And so that distance was measured in meters. And since it's a rate and time is measured in seconds, it's meters per second. Okey-doke. All right. Easy enough when somebody draws the picture for you. When you're trying to come up with a picture, it's going to take some practice. Let me check something else. Yep, we're on track. I hope to get one more done today, and I think that's what we have time for. Number 24. And I have an animation for that. Okay. I found in GeoGebra an illustration, an animation of a boat being pulled into a dock. I edited it just a little bit because the problem we're fixing to do has the rope 12 feet above the dock, or 12 feet above the surface of the boat. So that's why I changed the height to 12. Let's see. As the boat's being pulled into the dock, X is the distance of the boat from the dock, and Y is the amount of rope out. All right, somebody's up here at point E. pulling on that rope or twisting a handle to row that boat in. Y is the amount of rope out, and X is the distance of the front of the boat from the dock. The height's always 12. So kind of like the ladder, if I'm pulling that boat in at a constant rate, which one of my rates is going to be constant, dy over dt or dx over dt? If I'm pulling the boat in at a constant rate. Yeah, that's the rate at which I'm pulling in the rope. dy over dt is going to be a constant, and dx over dt is going to change the closer the boat gets to the dock. The closer the boat gets to the dock, the faster x is going to change. Pretty much for the same reason as the ladder, the height of the ladder sped up as the ladder fell. So let's see the problem. A boat is pulled into a dock by means of a winch. And that's not a hybrid woman. That's not that kind of winch. It's a gear with a handle attached. Ropes pulled into a dock by means of a winch 12 feet above the deck of the boat. Let's see where to put that on my picture. That's my 12. That's my constant 12 feet. And again, don't label anything on your picture that's changing. That 12 is not changing unless the lever, the pulley falls off its post. Write an equation relating the amount of rope out to the distance of the boat from the dock. Well, let's use X. It's a good thing to use for horizontal distances. And that's the distance of the boat from the dock. What can we use for the amount of rope out? You know what? I'm a little hesitant to call it Y because Y usually indicates a vertical distance, and we know that vertical distance is 12. Technically, it doesn't matter, but I'm going to reserve Y's for vertical distance. I'm going to use, I think I used L for the length of rope or A for the amount of rope, whatever you want, just as long as you understand what it represents. So write an equation relating the amount of rope out to the distance of the boat from the dock. What equation can I come up with looking at that picture? So what's my equation? Yep. X squared plus 12 squared equals L squared. Leg squared plus leg squared equals hypotenuse squared. Find an equation which relates the variables in terms of their individual values and their rates. If I want an equation with rates in it, how do I get that? Differentiate with respect to time. The derivative of the left-hand side with respect to time would be what? Well, 2x times dx over dt, derivative of 144 is 0. Derivative of the right-hand side is 2L times dL over dt. And again, if I just wanted to have an equation with smaller numbers in it, I could divide both sides by 2 and have x times dx over dt equals L times dL over dt. And then I have a two-part problem, kind of like number 20 was with an A and a B part. The A part says the winch pulls in the rope at a constant rate of 4 feet per second. Which rate is that? That's the change in L. So given the L over dt is 4. Determine the speed of the boat. We don't have anything about speed of the boat. It's how fast X is changing. How fast the boat is approaching the dock is dx over dt. And the other thing we're given is determine the speed of the boat when there's 13 feet of rope out. What's that 13?
L.
That's L. I'm going to substitute those values into this equation and have, oh, I don't have anything to plug in the place of X. Use the Pythagorean theorem. I'm going to have to, I can put it right here. When when L is 13, X would be square root of 169 minus 144. That's square root of 25 or just 5. When L is 13, X is 5. So using this equation, when X is 5 times dx over dt equals my 13 times my dl over dt, which I knew to be 4. There was something I didn't pay attention to, and that was the sign of each rate. Should dx over dt be positive or negative? Negative, because that distance is getting smaller. What about dl over dt? It'll be negative also because that rope is being reeled in shorter and shorter. So I should have said right here, dl over dt is -4. Watch out for that. And that means dx over dt is -52 fifths, or -10.4. What are the units on that 10.4? That's feet per second. And how can something be going -10.4 feet per second? It just means 10.4 feet per second getting closer and closer to the dock. So X is smaller and smaller. And we won't finish the B part, but let's find out what we're looking for and what we're given. Suppose the boat is moving at a constant rate of 4 feet per second. What's that? dx over dt. And I'm paying attention this time. Should that be +4 or -4? That's -4 because the boat's being reeled in. Determine the speed at which the winch pulls in rope. What is that? That's the rate at which the rope's getting shorter. So dl over dt. And what are we given? When there's a total of 13 feet of rope out, what is that? When L equals 13. Do you see how much this sentence clarifies things? Write that sentence in your homework. Use the words, given this, find this, when that. If you draw a picture and you can write that sentence, I bet you get the rest of it right. Okay, I decided not to take up 1 through 13 odd today just because they were so simple. I will wait until today's Wednesday. I will wait until Monday and take all of 3.7 up together and then pick 3 of them to grade. Now, see, I didn't mean to tell you I was going to wait till Monday. That doesn't mean you do all this homework Sunday night, you still do what you need to do tonight. Where is that homework written? Yeah, it's on the last page. Oh, right here. Now, here's how the homework is broken down. 4 problems tonight.